floor is mine. Thank you, Professor Hans van Dijk. Good morning, everyone. Well, you heard my name already, Weer de Vet. So I have been working for over 12 years now as a technologist at this company, Oasen, which I will introduce a bit later. I will tell you some practical aspects and some background information about the treatment of a very special type of raw water, which is actually in between surface water and groundwater, riverbank filtration. I want to acknowledge some of my co-researcher in my PhD research, Casper van Genuchten, which is also a colleague from Oasen, and the two professors, Hans van Dijk and Mark van Loosdrecht, with which I cooperate. Mark van Loosdrecht is a microbiotechnologist. Okay, what am I going to talk about? Of course, I will introduce riverbank filtration and my company shortly. I will tell about some of the factors determining the quality of riverbank filtrate. And then, of course, I will focus mostly on some aspects of the treatment of this groundwater, riverbank filtrate groundwater. And I end, well, as I should, of course, with the conclusions. My company, the company of Oasen, this is a company that produces drinking water to the southeast of where we are now, about 30 kilometers from here is the city of Gouda. My company produces drinking water for about 750,000 consumers and some industries, and that means that we produce about a bit less than 50 million cubic meters of drinking water per year. What else do I want to tell here? Not much, I think. So this is an aerial picture of one of our treatment plants, and well, maybe you see it, maybe you don't. But you can see there are lots of buildings built together, and actually these are all separate treatment processes. So the treatment of riverbank filtrate is quite an extended process. My company Oasen lies in the blue area of the Netherlands. The sheet already says it, so I don't have to ask you what it is. But the blue area is the area of the Netherlands that is below sea level. This means we are in a polder area, so we have to pump the water out actively, the water that falls by the rain, but also that infiltrates from the rivers that flow through this area. And this infiltration from the rivers, well, that's bank filtration. When you look at riverbank filtration, I already said that it is something intermediate between surface water and groundwater. And there has been a lot of discussion in the past, and well, it still goes on every now and then, about whether riverbank filtration is good. Is it better or is it worse than surface water treatment? So direct treatment of surface water. And well, there are some disadvantages of using riverbank filtrate. One of them is that, well, it's a natural process. So it just happens naturally, and you cannot stop it. So for instance, when you have a peak of pollutants in your river water, it will infiltrate. You can change it a little bit, but you cannot stop it. So this is one of the disadvantages. When you have surface water treatment, you can say, oh, I wait with intake of this water until the peak of the pollutants has passed, and then I restart again. But with riverbank infiltration, you cannot. The other one is that, especially when you look at peaks of pollutants in surface water, when it has passed in the river, then you have good water again in the river. But in your infiltrated water, it will lag for a long time. So you will find it in your groundwater, sometimes even years after that has been in the river. Of course, there are also advantages, and there are quite a lot of advantages. And the main advantage, I think, of riverbank filtrate over surface water is that it has a very good and constant quality. So the peaks that are in the surface water, they are lowered by different processes like dispersion in the ground, but also the difference in residence time from the surface to the groundwater treatment and soil characteristics. Sorry. And one of the other advantages is that you have a lot of removal of pollutants in your infiltration system. It's very clearly that the suspended matter is filtered out, but you see also removal, very good removal of pathogens, and removal of well, all kinds of pollutants, organic materials, and also micropollutants. So this is a very big advantage. It is still a discussion that sometimes goes on, but in the years, the 80 years of the last century, there have been some big spoils of well, pesticides and micropollutants in the River Rhine. And at that time there was a German professor called Holuta, who well, sort of said with relief, well, if this riverbank infiltration had not been here for already more than 100 years, then we would have invented it now. Because there was a long and very high concentration of micropollutants in the river, and if you would have had to treat it directly from the surface water, then you would really have had a problem in your drinking water production, because these high concentrations were hard to remove at that time. Well, in the riverbank filtrate, it's much easier. Well, this is a bit about the infiltration, the riverbank filtration discussions going on about that. I will not talk about the micropollutants anymore at this moment, but I will concentrate on the macropollutants. Yeah? So not the organic pollutants, but the inorganic pollutants that are present in these kinds of waters. And how do they come in there? Well, this is a scheme of the aquifer in our polder area. At the left you see the River Rhine, and you see the water infiltrating in the aquifer. This is the first aquifer, sometimes also deeper aquifers, but let's focus on the first one. You see that this aquifer is confined by two impermeable layers, so one at the bottom, one at the top. So it's actually sort of well, in a safe place in the ground. This water I will call RBF, riverbank filtrate. But there's also another part of the water that is part of our raw water, and that's of course the water that falls on top of the polder and just infiltrates through the impermeable layer, well, not totally impermeable layer, but the layer on top. And it also goes to our wells. I will refer to this water as polder water next. Well, this polder water has very specific characteristics. You should think that this area, this polder area, is actually, well, has been for centuries sort of a wetland. So it's really, well, this is a really typical Dutch picture, of course, with the windmills. But it's also, well, more or less the situation as it was 200 years ago in this area. And now we have better irrigation, or better, removal of the water. So the surface is dry now, but still the land is very wet. And this has led to the accumulation of peat layers in our area. So on top of our aquifer, we have a peat layer of about 10 to 30 meters of decomposing plants, as you see here. Now, when you look at both types of water, so both the river infiltrate and the polder water, you see that the water changes during its path from the surface to the well, to the river, to the well where we extract the water. So both the waters, the rainwater and the river water, they start as aerobic water, and then the first process you see. Actually, I'm going to tell about a series of reduction oxidation processes that take place. And the first process you see is that all the oxygen is being consumed. There are organic matter in both types of waters, and this organic matter is oxidized by oxygen in the first case until there's none left. So then you have anoxic water. Well, the next step is that all the nitrates, so the nitrogen-containing oxidizing material is being reduced, and all is being removed. Well, then you have some other steps in it. So you have the reduction of deposits of iron and manganese, which are in the soil, the deposits in the aquifer or in the top layer. And these iron and manganese, they get reduced and in solution then. And there are two other substances that are being reduced, and that's actually sulfate. And the last one is that the organic matter is being reduced into methane. So this is really the last step of this process. And all these processes, they actually occur in order. So not at the same time, but one by one. For oase, we actually, when you look at the two types of water, so the riverbank filtrate and the polder water, the riverbank filtrate is about at this level. So there is manganese and iron in all the water that comes from the river. And when you look at the water that comes from the top, the polder water, then you see there is methane in it. Well, then other process that's very important when you look at riverbank filtration is that you have the mixture of these two types of water, but you also have this mixture at other riverbank filtration locations. So I give an example of actually the biggest riverbank filtration treatment plant in the Netherlands, which is in the south of the Netherlands, in Limburg, by the WML. At the hill, this is a different situation, so you don't have polders there, but you do have infiltrating river water, and you do have rain that infiltrates in the more sandy area there. And you see a very nice result of this. Here you look into one of the wells where they extract the groundwater, and you see that one half is totally clear of the well filter, and the other half contains iron oxides deposits. Well, here you can clearly see that there's mixing of two types of water. So from the top there is aerated water coming in, and from the bottom there's reduced water with iron. So from the land coming in. Well, at the water we see the same process, but you see it on other parameters. I told you that in one type of water you actually don't have sulfate and methane at the same time. Well, when you look at the wells of one treatment plant of oase, I have sulfate and methane on the two axes here. Then you see in almost all these wells, you both have methane and sulfate present. This means, and this is caused by the fact that the water in these wells is mixed. So it's not the original groundwater, but it's a mixture of two types of groundwater in the wells that occurs. How does this happen and how does it work? Well, this is a simple picture, and I'm going to tell no more about it than this. It mostly has to do with the residence time of the infiltrated water from the river to the wells. When you have a well field, for instance like this one, which is loodrecht, perpendicular on the river, you can understand that the residence time in the aquifer is shorter for the first well than for the last well. And this means that the part of the water you extract will be, for a bigger part, riverbank filtrate next to the river than farther away from the river. I could tell a lot more about the groundwater, but I will now go to the treatment of this groundwater. At the oase, generally this is the type of water we extract. So this is the mixed water. It's purely anoxic, anaerobic. It has a more or less neutral pH, so it is not acid, but also not basic. And it has, as macro components, it has all the macro components: methane, iron, manganese, and ammonium in it in relatively high concentrations. So when you remember the lecture from Professor van Dijk before this one, and you look at these, sorry? you look at the concentration of ammonium, 1 to 40 ppm or milligrams per liter, then you already know that you cannot treat this water with only wet filtration, because you need a 3.5 milligrams of oxygen per milligram of ammonium to remove, and then you would have, well, either a system with pure oxygen or a high pressure system, and that's not the way we normally do it. So this is one of the things I will come back to. Well, the other thing is you can remove these substances by a whole lot of processes. Of course, I would say membrane filtration is one of the possibilities, especially nanofiltration. But you can also think about stripping. Well, Professor van Dijk already said that for methane this is a good option, but for ammonia it's not really feasible, because you really need very high energy input, and then still it's not effective. When you look to iron and manganese, actually, well, when you don't look at ion exchange or membrane filtration, the only way to remove these substances is by oxidation. You first have to oxidize the forms that are present in the groundwater before you can remove them. Well, this process, you can actually remove all these substances by first oxidation, and these oxidation processes can be either chemical or microbial. So there are a lot of possibilities, and in my next slides I will give you some indications of what might really happen in food practice. Well, this one I don't, well, you saw it before this morning. So this is a general scheme of groundwater treatment, and well, it is much like a treatment system of the riverbank water, with the aeration and the filtration as the central steps. Well, you see this is wet filtration, submerged filters. And at the Oasen, because of the high oxygen demand of the water for treatment, we cannot use the wet filters, but we use dry or trickling filters. Well, I will show you some pictures afterwards. It is still a filter, but you don't have water on top of it. It's just water trickling through. So on top of the filter, you directly spray the groundwater with all the pollutants in it you want to remove. You add a lot of air, and actually we add with an RQ of about 10. And then, well, the water trickles together with the air, and you get conversion of ammonia to nitrate. I will come to that later. You get the depositions of iron and manganese, so they're oxidized and deposited in the filter bed. And the methane, well, here I put it totally in the air, but it can also be removed by biological processes, and then in some way is also being deposited in the filter bed. And I will come to that later as well. Well, these are some pictures of how this looks in practice. Yeah, well, it's not very imposing, but it's all around in the Netherlands. So this is actually the central step of groundwater treatment, also at the Oasen. You see direct spraying of the raw groundwater on top of a dry filter bed, here as well. Well, in the treatment of the micropollutants I mentioned, methane is normally not a problem itself. The removal is not a problem. But the other components, so iron, manganese and ammonium, do pose problems. And for Oasen it is mainly nitrification, the removal of ammonium, that poses the biggest problems. Well, this process, when you don't use the stripping, is actually well, the only practical feasible process you have. You can use a very strong oxidizing agent like chlorine dioxide, which you do in the United States, for instance. But you would need quite high concentrations of this. And in the Netherlands, we do not work with these kinds of strong chemicals for these purposes, at least. So the only process that you can remove ammonium in the Netherlands is biological nitrification. This is a two-step process. You first have to convert the ammonium into nitrite, NO2 minus. And this is done by the specific groups of microorganisms. Maybe you have heard of them, maybe not. But the Nitrosomonas bacteria is one of the main bacteria known to do this. But which is also very nice is that there's a totally different group of microorganisms which are not bacteria. So you have bacteria, but you also have other domain in life, and that's called archaea. And they are also active in this field of work, I would say. This has been shown only 4 years ago for the first time by new molecular techniques, so DNA techniques. So this is a new development, but I think you will hear more from that. So these organisms, they are active in drinking water filters as well. Well, then you have the second step. That's a nitrite oxidation from nitrite to nitrate, NO3 minus. And when you know in literature you read a lot that's being done by the bacteria of Nitrobacter, which is actually the case. But these bacteria usually work under conditions with high ammonium and high nitrate concentration. So, for instance, in wastewater treatment. In drinking water treatment, you have low concentrations of ammonium and nitrite, and then you see that, well, it's another type of bacteria, another species of bacteria, Nitrospira, that's doing the job. Here's one picture of them, and it's good to know that these organisms are so-called autotrophic microorganisms, and that means that they don't use an organic carbon source like glucose for their growth, but they use an inorganic carbon source, which is in this case bicarbonate. And to build biomass from inorganic carbon is a lot less energy efficient. It costs a lot of energy, and then if you know that oxidation of ammonia is also not giving much energy, then you can understand that these bacteria grow really slowly. So this is a slowly growing organism. And, well, that results in this situation in an average groundwater filter. There's a lot of iron and manganese deposition in it. And only, well, maybe 1 or 2% of this mass is biomass. So can you really look for a needle in a haystack when you're going to look for biomass in this system. But they are there and they're doing a very important job. Now for the problem we have at Oasen with the nitrification, I'll give you an example of one trickling filter. We follow this trickling filter over the period of 3 years. And on the vertical axis, I will show you what the ammonium concentration in the effluent of the filter will do in the 3 years. The horizontal dotted line is the average of the influent concentration. In reality, it fluctuates a little bit, but it's more or less average in time, constant in time, sorry. Well, the first year, you see that the effluent concentration is, well, near to the influent concentration. There's actually not much going on in this filter. The nitrification is very bad. Then at this line, Oase says, well, we don't take up with it anymore. We're going to take all the filter material out. We put a new filter sand and we just start anew. And we do that oftenly. And then you see this. So nitrification really goes quickly. You see the ingrowth of bacteria. And well, after 3 to 5 months, you see that almost all the ammonium is being converted. And you have very good nitrification, almost complete. And then you think, well, okay, I can rest and sit back now, it's okay. But unfortunately, it is not. So this is the next 2 years. And this is, well, I would say, unfortunately, a picture we always, or in many cases, see. So this is structural. And after 3 years, you are, well, at the beginning again, and you can start by putting in new sand, which is, of course, not very good for the continuity of your process. Well, we have been doing research for this for over a decade. So there has been a lot of research and there are a lot of things you can think and talk about. But I will focus on 2 aspects. And they have to do with competition for these that these nitrifying microorganisms might find in a trickling filter. So I'm going to focus on other microbial processes that might take place in a trickling filter. Well, does anyone know what this is? This formula? No idea? I'm going to talk about microorganisms. So, any idea what this molecular formula might be? Well, I can wait. I still have 20 minutes. Do you think this is a substrate, something that they can eat, the bacteria? Well, maybe next year. No, maybe at one other point you can tell. But this is the general formula for bacteria, for microorganisms. So when you see what elements are in it, well, you see that it's mainly carbon, hydrogen, oxygen, nitrogen. But there are also some, to a lesser extent, some other elements in it, like phosphate, sulfur, potassium, manganese, and of course a whole lot of trace elements as well. But I have not put them in the formula. When you look at the system of Oasen, you see, well, they use bicarbonate. This is groundwater, well-buffered groundwater. There's a lot of bicarbonate in the water, so that's not the problem. When you look at oxygen, we have a trickling filter. There's a lot of exchange of oxygen in the system. So oxygen will probably also not be a problem. N comes from ammonium. Well, we do not remove the ammonium, so well, I expect that's also not a problem here. Sulfate, potassium and manganese, they are all well available in groundwater. So we do not expect there's a problem. But there's one element that might pose a problem, and that's phosphate. You see there's not much in a microorganism, but there still is some. And the amount, the concentration of phosphate in groundwater is not high, and it's also being removed during the treatment of the system. So this is a parameter that might be of interest. So I'm going to focus now on two other removal processes, methane removal and iron removal in these trickling filters, and see if you can find clues if there's really the competition over this phosphate that is posing a problem. Well, first, methane. I said you can remove it by stripping, and you can also do it biologically. If you do it biologically, then you will get growth of a lot of biomass, because well, methane is an inflammable gas. It has a high energy content. So if you burn it, if you oxidize it, you get a lot more biomass in it. So competition could play a role then for phosphate, and also well, just clogging of the filter. You get a lot of growth of biomass in the filter. So at the WAS we looked at quite a lot of systems, filter systems, to see if we could find if it was a biological or a physical process, the removal of methane. Well, I was going to ask you what these systems were, but you already know, so different kind of aeration systems are very good for removal of methane. Spray aeration, plate aeration, cascade aeration, tower aeration, and vacuum aeration. Actually, if you design them well, they're all effective in stripping methane. So what we did at Oase, we took a water treatment plant that had big nitrification problems. And well, we looked at the filter that just treated groundwater directly, and you saw this when you looked at the nitrification. So after, well, say 3 to 6 months, you see that the nitrification is going back, is falling back, and it's not totally anymore. And then we took a similar filter at the same treatment plant, and we posed a vacuum treater in front of it to remove almost all the methane. And then this was the result. So in the beginning there are some differences, of course, but actually for me this was clearly there was no difference at all. So it did not work. Of course, we were a bit surprised by that, and we were wanting to know what really happened. So we did some extra research in what happened to the methane. We made good balances of methane, and not only in the water, but also in the air that came out of the filter. So these are the measurement devices we use for that. And we developed a specific technique so we could measure this very accurately. And then we found that most of the methane was actually stripped out of the water. And we also confirmed these results by measurements of direct microbial activity, so methane oxidizing activity in filter beds. And we compared these two systems. And the activity, methane oxidizing activity in the filter with pre-treated from vacuum degassing, sorry, was not much lower than in normal filter. So there was not much microbiology doing the methane removal. Methane itself you cannot measure in the effluent of a filter. It's always totally gone. So you have a removal efficiency of 100%. But that doesn't say if it's microbial or physical. But when you compare methane removal to carbon dioxide removal, you see something interesting. Carbon dioxide, you heard this morning, is removed much worse than methane by aeration. And you see the lower lines, the red dots, is removal efficiency for carbon dioxide in the vacuum stripper, which is actually, well, for this system at least, quite bad. It was less than 20% removal efficiency. But when you look at the trickling filter, then you see that it's well, in most cases about 80% removal efficiency. So a much higher efficiency for carbon dioxide removal. And at that point we concluded that the trickling filter was actually a very efficient co-current plug flow gas exchange system. Yeah, so, well, we learned this and we concluded that vacuum stripping was not the solution for our problem. Well, then the other one. There's also manganese. I will not go into manganese at this moment. There has also been results, so if you ever have any questions about that, you can come to that to me about that later. But I'm going to focus on the iron removal a bit further. I don't know if you already know about iron removal. Have you had? Yeah? So you know already quite something about it. Well, maybe I'll tell some double things then. I already told you that for iron removal you first have to oxidize the dissolved reduced form of iron in the water. Well, the first process that happens is you just put oxygen in the water by aeration, and then you see that the iron is oxidized. It's called a homogeneous oxidation of iron. And these iron flocks have a very low solubility, and they flock out. They form flocks, and then next you can filter them out of your system. The kinetics of this process has been very well researched, at least in laboratory. So mostly in pure water, and there is a very clear proportionality of the rate of iron oxidation with the square of the OH minus concentration, so it's related to pH of the water, to the oxygen content and to the concentration of reduced ferrous iron. And when you look at the graph, you can see that in this graph I will show you how quick the oxidation will go at different pHs. So this is 20 minutes, I think. Yeah, 20 minutes of time. And the first graph I show you is the maximum oxidation rate you can get at after well, this time of contact time in a totally aerated system, so a saturated oxygen system. And you see that after 10 minutes, well, it's only 60% maximum of the iron is oxidized. When you look at oxidation aeration systems, mostly the contact time is much lower than this. Fortunately, when you raise the pH, then you see that this goes much quicker, in theory. So when you look at the groundwater of Oasen, which has a pH of about 7.3, which is raised to about 7.6, 7.7 during aeration, you see that you're actually on these lines working, and you see that in, for instance, in 2 minutes time, that you can already have 80 minutes of oxidation of your iron. That oxidation of iron can pose a problem in reality was shown before at the treatment plant of Vitens in Flevoland. This Vitens, the Hardenbroek treatment plant with the cascade aeration. So the groundwater, anaerobic groundwater containing iron first is aerated by a cascade, and the oxidation rate of the iron was determined after the cascade. And you see, well, this part is the oxidated part. These are several sample points and sample times. But you can see that in general only about 10 to 15% of the iron is oxidized after the cascade. And then it comes to the filter. So then, well, you can already think, well, there might be a problem. Because if the iron is not oxidized, you cannot remove it. It just dissolves and flows through the filter. But fortunately, there is another mechanism known to remove iron, and this mechanism says that the iron does not first have to be oxidized, but can also adsorb onto filter material, and preferably filter material that's coated with a catalyzing coating, for instance with an iron hydroxide coating. And if you have this, well, you can remove the iron much quicker. So the rate of iron removal is increased by this process. This has been described by the researcher Sharma here in Delft about 10 years ago. So when we knew these two processes, we said, well, we're going to try both processes in the pilot scale setup and see if there is a difference in influence on nitrification. That's what you would do if you are a researcher. You know what processes are going on, and you just make a good pilot model of the situation. So what we did first, we made a system with drinking water as the base, so aerated water, almost with oxygen saturation in it. We added ammonium to make sure we have nitrification. And we added the reduced iron just before the spraying. A very simple system, you would say. And then you have actually a very short residence time, and most of the iron that is removed should be removed by this contact filtration. Well, the other system, you model in this way. You have the same filter system with the spraying on top of it, but then you put oxidation vessel in front of it. Sorry. With the contact time of 5, 10, 15 minutes. We took 15 minutes contact time, and you add the iron in front of this vessel, and you let it oxidize in the water. Yes? And then you have floc formation and floc filtration. Well, this is how it looked in practice. We're still working with this setup. And this was the result. Well, I should have taken the line at the bottom away. Then I could have asked a nice question, of course. But do you understand why the color difference is as it is? So this is actually the filter material we took out of the system after 4 months of operation with these two iron removal systems. You understand it? You can read at the bottom what it is. Left you have the system with the pre-oxidation, so with the floc filtration, and on the right you have the system with the adsorptive removal of iron. Do you understand why the difference occurs? Well, when you go to the right, yeah, it is called adsorptive oxidation. Well, adsorption means that the iron sticks to the filter material. Yeah? So then, well, you can understand that in time it will form some sort of a coating on it. Yeah? So this is the brown, the dark brown material is the coating with iron hydroxide. The other one, so this is the flock filtration system. You actually form your iron particles before the filtration, and this is just, well, ordinary filtration, I would say. Yeah? So you just filter off particles, and when you backwash your filter every now and then, these flocks are not attached to the filter material and are just washed out. And that's why it stays clean. Yeah? So this is, well, a very good illustration of the difference of the two removal processes, I think. Now, we did this test at two locations. One location was here at the TU Delft, and you should know that the drinking water here is from a4d4 company in Rotterdam, and it's made from surface water. And, well, this oxidation rate we got from 5 columns, from 5 oxidation columns with a residence time of 50 minutes. You see that oxidation is somewhere between 70 and 90%. So after the period of 50 minutes, the oxidation was quite good, was quite high. A bit lower than you would theoretically expect, but still quite high. And then we put the setup to a4d4 treatment plant. We did exactly the same pHs. And then we saw this. We saw that in the columns there was much less iron oxidation. This was really going much slower than it was here at TU Delft. Now I'm almost at the end. The probable mechanism that is occurring here is that there is a third iron removal mechanism. We have the two chemical mechanisms I described before, but there's also a microbial removal mechanism. And actually these bacteria take up the reduced dissolved iron, and they get their energy for growth from the oxidation of iron. In these two pictures, you see the sludge that is formed at the TU Delft. So with the high oxidation of sludge, you see that you get some sort of, it's a powdery-like, amorphous-like deposit. But when you look at the content of the oxidation column at Oasen, at the groundwater treatment plant, then you see that this is, I would say, typically biomass. So this is how bacteria grow with their extracellular polymeric substances. This is biomass. This is how it looks. And when you look at microscopic pictures in Lekkerkerk, you find all kinds of deposits which are formed by iron and manganese oxidizing bacteria. So these are leptotrix. These sheets you see are not the bacteria, but are very fine excreted iron hydroxide deposits. And you have a lot of these bacteria. What we also found was the Gallionella bacteria. I think they are even more beautiful deposits they make. It's the same material as the amorphous material you saw before, but well, it's of course a very structured way. It is being deposited. Well, to conclude, when you look at riverbank filtration, it has actually the good things of surface water, namely, you almost have an infinite capacity, and it combines it with the good things of groundwater, namely that it's of constant quality and has a high hygienic quality as well. On the other hand, there are of course backdraws of this. And one of the main backdraws is that you cannot control it totally, the system, and you also have the influence of mixing of different kind of waters in your raw water. Well, for the treatment, when you overlook the whole system, actually in the groundwater you saw that you first had reduction of nitrate, then you had the formation of iron and manganese, and then you had the formation of methane. In the treatment it's just the other way around. Yeah, that's good to remember. we have also seen that trickling filtration is a really robust and simple system that can actually remove all of these compounds combined, and it does this by several processes: stripping, bioconversion, filtration, adsorption. There are a lot of processes going on in this system. But we also saw that microbial processes in this system might be very, very important. So not only for nitrification, but also for the removal of the other compounds. And the last remark I'm going to say is that it might lead to competition over scarce elements, which is a problem for the nitrification in these systems. This is it. And if you ever want to do something nice and useful, then you can contact me, and we have a lot of nice internships or end works available. Thank you.